This next chapter is going to be about logarithms and exponential functions. And the reason we learn them together is because they're related. Actually, logarithms spawned because we didn't have an inverse for an exponential function. An exponential function is when you have a variable as an exponent. And we didn't really have ways to solve those, so we made these logarithms, which is just another way for us to write those exponential functions. Okay, so every function is going to have an inverse. Inverses are kind of the core principle of algebra. Okay, it's having these inverses, and that's what allows us to solve equations, is by using inverses to get rid of things so that we have just an x or a variable left. So logarithms are the inverse of exponential equations. So if I say y equals the log base a of x, that's the same as saying x equals a to the y. Okay, so notice where all these different parts are coming from. Okay, there's the x. So whatever if I have some base, so some number to some exponent, that base, okay, so the base from my exponent expression is still the base of my logarithm. And then we take the log of what it equals to equal the exponent. Okay, this is our exponent over here. And this is read as the log base a of x. So we can use this relationship to figure out what certain logs are going to be. All right, so if I have the log base 2 of 16, what I'm really asking is, my base is 2, so if I have 2, to what power is 16? So 2 times itself, how many times is going to give me 16? It's 4. So the log base 2 of 16 equals 4, because 2 to the 4 equals 16. Okay, so all we're doing is we're able to rewrite these from one version to the other whenever you want. So how about this? So I'm saying 10 to what power equals 1 over 100? Well, I know it's going to be a negative power because I'm ending up with a fraction. If it was a positive power, I'm just going to get bigger and bigger and bigger numbers. Since I'm ending up with this fraction, I know it's going to be negative. And the way I get 100 from 10 is squaring it. So that means x has to be negative 2. Because 10 to the negative 2 will be the same as 1 over 10 squared, which is 1 over 100. Okay, log base 3 of 1. So 3 to what power equals 1? Well, 3 to the 1 is 3. 3 to the 0 is 1. So x equals 0. Okay? In fact, anytime you take the log of 1, you're going to get an answer of 0, because 237 to the 0 power is 1. All right, how about if we're taking the log of 0? I'm saying 5 to what power equals 0? Well, no power is going to do that, right? Because to the 0 power gives me 1. That's not 0. To the first power gives me 5. And every power higher than that is going to give me a bigger number. If I start going negative, I would get 1/5. So there's no power that's ever going to bring you to 0. So this is undefined. Can't take the log of 0 ever. And that should be easy to remember. We can't divide by 0. Can't take the log of 0. 0 is one of those quirky numbers that just doesn't allow certain things to happen. Here I'm asking 4 to what power equals 4? Well, that's going to be 1. So the log base 4 of 4 equals 1. This one's undefined. This one equals 0. This one equals 0. This one equals negative 2. This one equals 4. Okay? So that's kind of the basic log property. We're going to get into some other things. If we talk about inverses again, Inverses cancel. So like multiplying cancels dividing because those are inverse operations. So if I have 5, I multiply by 2 and divide it by 2, I end up with what I started with. Okay, these two operations cancel each other out. They negate each other. Same way adding and subtracting negates each other. And you end up with just what you started with. Logs are going to cancel exponentials. So if I have a log of the same base as the base of my exponent, these two things cancel and leave just the exponent part. Same way if I have a base taken to a logarithmic power, I've got the same bases here, so these cancel and leave just x. Oh, this is not a 3. This should be an e. Okay, there's a new number. You guys have maybe seen this. It's on your calculator. Usually you'll notice an e to the x button. Well, that e is this number. Okay, it's an irrational number. It just keeps going on forever. And it's called the natural base. And so if we use e as the base of our logarithm, then we get the natural logarithm. And we abbreviate that just as ln, natural logarithm, or logarithm natural. Okay, so whenever you see ln, ln is the same as writing log with a base of e. Okay, these are the same thing. Now let's do some more examples. All right, here I'm asking to rewrite it in a different form. So remember, you're gonna take your base. Your base stays as your base. Okay? You're gonna take what it equals, that becomes your power. It equals what you were taking the log of. Okay, that's going from log to exponential. If I go from exponential, I'm just gonna do the same thing, okay? 8 is my base, it stays my base. But now instead of pairing the 2 with the 8, I pair the 64 with it, and it now equals the 2. Okay, and you can switch back and forth. 8 squared is 64. 3 to the 4th is 81, so log base 3 of 81 is 4. Here, this is using our inverse property. Log base 2 of 2, they're going to cancel, leave just the negative 1 equals x. And here, if I take the log base 8 of x, and that equals the log base 8 of 9, the only way you can have the same things equal to each other when they've got the same base is if you're taking the log of the same number. Okay, everything's the same about these except the x and the 9. Therefore, x has to be 9. Another way you could look at it is you could cancel both of these by raising them up to become powers of 8. Okay, and we'll get to this later. This is kind of down the road. This is how we start using these to solve. But basically that would cancel this and you would get just x equals 9. Okay, so that's the real basic properties of logs, and that should get you started in your packet.